So here you use mass balance concept to determine how much pollutant concentration is being accumulated in the system in a green infrastructures. For instance, detention pond as a function of pollutants being removed or discharged, and that reaction that happens inside. So as you know, we know this one that dm based on the equations that we learned, dm by dt pollutant accumulated uh, in the system is going to be d by dt. Mass is volume time concentrations. So this is basically volume time dc by dt from the system. And then amount of pollutants that coming in, dm by dt, is basically, you just remember that this is c times volume, and concentration, you can assume this is constant, that volume is changing or amount of water is being added, and then this is basically c times q. So this is basically here, and this is also for out. And then that means all you have to do is solve for the reaction terms. If you know the reaction term, you'll be able to predict it. And for that reaction, that could be adsorption, settling, all that. We can assume that most of the time is the first order reactions. That means change in concentration over time because of reaction is proportional to minus Kc. K is the reaction rate constants. And this is first order reaction because this is depends on just c to the power 1. So that means you can use this one. dm by dt reactions will be d by dt volume time concentrations. That means volume is of the reactor is constant, so that means dc by dt reactions would be volume. This is minus kc multiply kc. So that means this would be minus bkc. So that means in these equations, you can predict, you can put that as b minus k minus bkc, and you can solve for the reactions. Again, this k is a order of rate of reaction that will determine experimentally. Rate order of reaction determined experimentally. It could be first, second, third order, but most of the nature condition you can assume this is first order. So that's what I did. I put the value VKC, and so that is basically, if you have a one flow, one outflow, then Q in equal to Q out equal to Q. So you have a simplified equations. So this is basically a pond of volume P, and there is a flow rate coming in, but same flow rate leaving the system. This is C in, and this is leaving the outside. And here you can make assumption that the reaction happened inside the pond and is completely mixed. That means the moment the pollutant get inside, it quickly reacted, and whatever the reactions happens instantly, and the concentration decreased to C, and that's what the concentration leaving the system. And the concentration doesn't change because there is no reaction outside it. So if you make those assumptions, you can solve for this one. This is a first order first linear equations, and there is a solution for that. You can search online how to do that one, and this is something is going to find. And for the steady state, the concentration doesn't change in the system because whatever coming in there is no change in concentration. So that means for steady state, you can assume dc by dt or no change in concentration inside the pond. Whatever pollutant is being added is being removed by reactions and dumped outside. So in this case, QC in minus QC plus VKC equal to 0. So that means you can predict C by QC in divided by Q plus BK. So this is where you can predict the concentration of effluents if it's a steady state reactions. Steady state is basically what's the net amount is leaving the system, that you can do that when you average the concentration over years. So let's see how we can use this for this example. Here it says that a lake contains a certain amount of water. It's fed by river discharge at certain rate. Evaporations across the surface water takes away a certain amount of water, and so that means you know what is the Q downstream. And again, evaporation doesn't take any pollutants out, so you can assume that more pollutants move through the system over that. Upstream river is polluted, a concentration of pollutant is 6 milligram, inside the lake is this. So basically you are calculating, it doesn't say anything, what is basically C downstream. That's the question it is asked. So again, you what is given here is that 1 inflow and 2 outflow. Okay. So this is Q up, C up, this is Q evaporations, this is Q down, C down, and this here concentration evaporations, the water, evaporative water has no pollutants. So now, and then there's a reaction happen here, and that reaction decrease the concentration to C, and there is a rate at Q, and this is the volume of V. So based on the mass balance, you know that if it is a steady state, you know that dV by dC is equal to sum of all Q in C in minus sum of all out C out minus reaction terms. So B dC by dt reactions. So if you write this one, everything that's come in is basically Q up, C up. Everything that leave the system is C evaporations, Q evaporations minus Q down, C down. Here you can make assumption that C down is same as C inside the lake because then there is no reaction outside. So whatever water coming in must be the water that is inside the lake. So you can write C down and then minus here, and this term would be first order rate constant. So you can say that this is minus, this is a Kc. This minus term already exists because accounting for the fact that this is a reaction decrease the concentration. So you can just write that. Or you can write that P here, and then this is basically minus Kc. So when you put this value, and for a steady state, this concentration doesn't change over time. So that means in the system, net change in 0. So that is for steady state. If you put that one, and this is concentration is 0 for evaporations, there is no pollutant move the system because of evaporations. Now we can solve for the C value. So that means if you rearrange the equations, C in the outflow or C out or C down equal to C, which is basically going to be Q up, C up divided by Q down plus B K. Q up is given is a 9 times 10 to the power 4, 9 times 10 to the power 4 meter cube per year, and this is a C up is a 6 upstream river is 6 milligram per liter, 6 milligram per liter, and then you have a Q down is basically 8 times 10 to the power 4 meter cube per year, and then you have a volume is given 2 times 10 to the 5 meter cube, so this is 20 times 10 to the 4 meter cube, and K is basically is given somewhere 0.1 per year, so times 0.12 by year. There you go. If I write this one, let's see, put this one. This is basically plus B is 20 times 10 to the power 4 meter square or meter cube times 0.12 by year. So everything cancel out, so you'll get a milligram per liter. So this is how you can predict the concentrations. And the same equation you can use to predict when there is no reactions, when there are just a two stream combined with the river, so that it is being mixed. So how you can do that? So think of this way: you have a storm water. This is, let's say, storm water coming in. Storm water. You have a flow rate Q storm and the concentrations. And river is basically Q upstream, and there is a concentration upstream, and they mix together here. And then the instant reacts, there is no reaction, they are just mixing, and the concentration become diluted. The stormwater concentration diluted. So then it's become Q down and C down. So here you can use these equations to solve it. Basically here the assuming steady state is instantly mixed, there is no change. This is basically all the sum of concentration coming in has to be sum of concentration out. So again, this is steady state. Steady state. That means you have QC in has to be QC out. All the flow rate that coming in must be all the flow rate leaving the system, and that the pollutant is conserved. When you do that one, you can write this one. There are two in here in this system. So this is Q, one is stormwater. So this is flow rate of stormwater, then concentration of stormwater plus flow rate that's coming up upstream times C up. These are the two in flow rate. They mix together and the same amount of pollutants flow in the downstream river. So that basically Q down times C down. So here most of the time you are solving for C down. And so C down is going to be equal to QS plus QSCS plus Q up C up divided by Q down. And again, Q down, you can predict what is that? Basically, two pipe mixed together, so the water is going to be the same water. So you can assume that Q up plus QS. The reason is basically two water being mixed together. So there is no water loss, so that means the net flow rate will be addition of everything that's coming in beforehand. So this is going to be QS plus Q up. So by using this equation, you can predict when the stormwater is mixed with a stream and river, what the pollutant concentration will be, assuming there is no degradations. So this is example. This is a sphere pipe or this think of storm, and there is a concentration all that given, and is saying what is the concentration in the downstream. So again, based on the equation, say mix is going to be whatever all the pollutants that's coming in here plus all the pollutants coming in upstream, they are combined together. So mass of pollutant coming in the sphere system is CSC times QSC. Mass of pollutants in the original stream is basically concentrations times flow rate stream, and then basically Q mix. Q mix is given. So you can just put those value, and that's all the numbers are given. So you don't really know, just put the value, and then you'll get the number. So that means ES is 1 point. I can write this one 1.2 gram per liter times 200 liter per minute, and then plus 20 milligram per liter. So again, here you have to change the concentration. So 20 milligram is 20 milligram by 1000 is 20 this gram per liter times 2 cubic meter, 2 cubic meter per second. So again, here you are seeing the different units. So you just have to change those units. That way you'll be able to predict that. You mix is QST plus QSC. So that's a 2 cubic meter per second plus 2000 liter per minute. Again, this one you have to change per liter. So that means 1000 liter is same as 1 cubic meter, and 1 minute is 60 seconds. When you do that, you change to meter cube per second. And same thing, you can do it here. Meter cube per second, you can do change that to meter cube per second. And here you have grams, then the answer will be gram per liter. So you can use this kind of formula to predict the concentrations in the mixing factor.